This lecture is part of an introductory undergraduate course on complex analysis and will be about finding roots of complex numbers. So for real numbers, you can always take a square root of a real number, and this is always a complex number. If the real number is positive, like 5, then the square root of 5 is already a real number. If the real number is negative, then the square root, you can take a square root to be I times the square root of 5. So every real number has a complex number that's a square root. And the problem is, do complex numbers have square roots? For example, can we find a square root of 2 plus I? And there's no particular reason to stop with square roots. We can ask, does a complex number have a cube root or a fifth root or whatever? And the answer to all of these is yes. And in order to understand this, we need to understand the geometric meaning of multiplication. By the way, it's not at all obvious that if we just add in the square root of -1, then we can automatically find square roots of anything. For example, if we started with the rational numbers instead of the real numbers and added in the square root of -1, then there would still be lots of things that didn't have square roots. And even if we added in the square roots of all rational numbers, there would still be lots of numbers like 1 plus I that didn't have square roots. So fortunately, if we start with the real numbers and add in just the square root of I, then we'll see that we get square roots of all numbers. Now, in order to see this, we're going to express multiplication in terms of polar coordinates. So let's just recall what polar coordinates look like. So let's draw the complex plane, and in order to get a sense of scale, let's draw the unit circle. So we have 1i minus 1 and minus I. So it's conventional to draw the x-axis as the real line and the y-axis as the multiples of I, or the imaginary line, and we put I above the real axis rather than below it for no particular reason. And now suppose we've got a complex number z, which is equal to x plus iy. Well, we can write z in polar coordinates by taking this angle theta and by looking at the distance from z to 0, which is r. So r is equal to the absolute value of z, and tan of theta is equal to y over x. And conversely, we see that x is equal to r times cosine theta and y is equal to r times sine of theta. So these are just the usual rules for conversing between rectangular and polar coordinates. And now you notice that if we take the numbers of absolute value 1, so let's draw numbers of absolute value 1 here in red, these actually form a group. Well, what do we mean by a group? This means it's closed under multiplication and taking inverses. So if z1 is equal to 1 and z2 has absolute value equal to 1, then z1, z2 also has absolute value equal to 1, and the inverse of z1 has absolute value equal to 1. So we can multiply and divide points on this red circle group. And we also see that any complex number z can be written as a point on this circle group times a positive real number. So this point here is going to be cosine theta plus I sine theta, and the number z is equal to cosine theta plus I sine theta, all times its absolute value r. So we see that every non-zero complex number z can be written as a times b uniquely, where a is a positive real and b is in the circle group. So these are the numbers with absolute value equal to 1. We have to say non-zero complex number, because if we allowed 0 complex numbers, then this wouldn't be unique, because the argument of 0 isn't really well defined. So we can draw pictures of these two groups here. So here we have the positive reals. So that's these bits here. And here we have the circle group, which is the red circle there. So if you've done abstract algebra, you know another way of writing this is to say that the non-zero complex numbers, which we write as C times, that means you take the complex numbers under multiplication and throw away 0. So this is a product of these two groups. We can take the positive reals, that means the positive reals, and we take the product of this with the circle group. The circle group is often denoted by S1. S stands for sphere and 1 stands for one-dimensional. So a circle is a sort of one-dimensional sphere. And this means that we can, that there are two ways of doing multiplication in S1. So first of all, we can multiply them as complex numbers, or we can multiply them by adding angles. And what we want to check is that multiplying two numbers in the circle group by thinking of them as complex numbers is the same as adding the corresponding angles. So all we do is we just check both sides and see they're the same. So let's first of all take cosine theta 1 plus I sine theta 1 and multiply it by cosine theta 2 plus I sine theta 2. Well, we just multiply this out. We get cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I times cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. On the other hand, let's see what happens if we add two angles. Well, we need to know what is the cosine of theta 1 plus theta 2. Well, if you remember from your multiple angle formulas in geometry, that's just the same as cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And sine of theta 1 plus theta 2 is of course given by sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 1. It's very easy to get these the wrong way round. And now, if we inspect these, we see that this expression here is the same as this expression here, and meanwhile this expression here is just the same as this expression here. So this verifies that multiplication of complex numbers on the circle is the same as adding their angles. By the way, this means that complex numbers are really good for rotations of the two-dimensional real plane. So you can represent rotations as 2 by 2 matrices if you want, but it's sometimes easier just to represent them as complex numbers. So complex numbers are a good thing to use if you want to study rotations of the plane. Incidentally, quaternions that we mentioned briefly last lecture are good for rotations of 3-dimensional space and also even 4-dimensional space. In fact, we quite often need rotations of 3-dimensional space when you're doing things like if you're flying an aircraft over the Earth. Well, the Earth is a sort of sphere, so you need to know about rotations in order to figure out where your aeroplane should be going. And if you're playing 3-dimensional computer games, you quite often need to do a lot of rotations in 3-dimensional space. And navigation systems and 3D computer games quite often make heavy use of quaternions for handling rotations, because quaternions turn out to be the fastest and most efficient ways of doing this. So to summarize, to multiply two complex numbers z1 and z2, what we do is we multiply the absolute values and we add the angles they make with the x-axis. So the angle is sometimes called the argument. I don't really know why it's called the argument, but anyway. So for example, let's try and multiply two complex numbers without doing any actual work. So here I'm going to just write 1 and I to orient ourselves as usual. And let's take a couple of complex numbers. So I might take z1 to be up here, and I might take z2 to be somewhere down there. And what I want to do is to figure out where z1 times z2 is without doing any calculation. You just want to do it kind of by looking. So what we do is you first look at the arguments of these numbers. So the argument of z1 will be this angle here, and the argument of z2 will be this angle here. And so what we do is we add these angles, and of course you have to remember whether these angles are taken clockwise or anti-clockwise. So this angle means you go clockwise by about 1/8 of a revolution. So what we should do is we should take this angle and go 1/8 of a revolution in that direction. We get something approximately like that. So z1, z2 is going to lie somewhere on this line because we have to add the angles. And now we need to know where on the line it is. Well, z2 has absolute value a little bit less than 1. So the absolute value of z1 times z2 will be a little bit less than the absolute value of z1. So it'll be sort of around here somewhere. So z1, z2 will be somewhere around here. So you see you can actually multiply complex numbers just by visually staring at them and figuring out where they are without doing any algebraic calculations at all. There's one slight warning I should put in here. If you're trying to multiply complex numbers on a computer, there's a sort of very standard mistake that you can make. So let's take a complex number, and we've got a complex number z, and we're trying to convert it into polar coordinates, and so z is equal to x plus iy, and we see that the absolute value of z is equal to the square root of x squared plus y squared, and tan of theta is equal to y over x, because there's y and there's x. So we can figure out theta as the arctan of y over x. Well, if you do that, you will quite often get the wrong answer, because this formula here is incorrect. The problem is that there are several different angles whose tangent is y over x. For instance, if we look at this angle here, then the tan of this angle is the same as the tangent of this angle. And these two angles differ by pi. So the problem is that tan of pi plus theta is equal to the tan of theta. So you can't work out theta by taking the arctangent of y over x in general. In fact, on most calculators and computers, the arctan defines that minus pi over 2 is less than or possibly equal to arctan theta is less than or equal to pi over 2. So if the real part of z is less than 0, you have to modify this formula by adding or subtracting a factor of pi to theta. The same problem, of course, occurs when you're just working with general polar coordinates. In fact, a fair number of computer languages have a function called something like a tan 2 of x and y, which will actually correctly calculate the angle you need for this thing to be in polar coordinates. So that's just a warning. When you're converting complex numbers in rectangular coordinates to polar coordinates, you can't just go around mindlessly using the arctangent function. So now let's talk about square roots. So what about the square root of z? Well, we can easily find the square root of z because this has half the argument and its absolute value is the square root of the absolute value of z. So this almost instantly shows that every complex number has a square root and even tells you how to calculate it. So let's just draw a picture of this. So here's 1 and here's I, and suppose I've got a number z up here, say. So how do we find its square root? Well, we convert it into polar coordinates and we work at this angle theta, and so this is an angle theta, and what we do is we just divide theta by 2. So this angle is theta over 2, and we take a point here whose distance is the absolute value of z, and then we have to take the square root of the absolute value of z. So the square root of z will be here. Its argument will be half the argument of z, and its absolute value is the square root of the absolute value of z. And as you can always take square roots of positive reals, and you can always take half an angle, this shows that square roots always exist. Well, there's one slight problem. The square root of z, z has 2 square roots. Because if we take one square root, then minus that will also be a square root of z. Now for the real numbers, every real number has 2 square roots, but we have a convention that we always take the positive square root, and this gives us a nice continuous square root of positive real numbers. So we would like to do something like that for complex numbers. So problem, choose a square root of z. We want to choose a canonical square root of z to get a continuous function. Well, let's try and do that. So let's start off by choosing the square root of 1, and we're going to make the square root of 1 equal to 1, of course. It'd be kind of stupid to make it equal to -1. And now we have to choose the square root for other complex numbers so that we get a continuous square root. And what we're going to do is we're going to send out an explorer along the circle in a northward direction, well, an upward direction or whatever, and this explorer is going to figure out what the square root of each number of absolute value 1 is, and they have to make this work in a continuous way. So what about the square root of something bigger than 1? Well, the square root could either be there or over there, but we want it to be continuous, so let's take the square root that's down there. And if you move off a bit here, its square root is going to be there. So I'm drawing a line here from z to the square root of z everywhere. And when I get up to I, its square root is going to be sort of down here. And when I get up to here, the square root is going to be somewhere around there. And when I get to -I, by continuity, the square root, so when I get to -1, the square root will have to be I. So we had 2 choices for what the square root of 1 could be. It could either be I or -I, and we see that in fact we have to define it to be equal to I. Otherwise the square root wouldn't be continuous. Okay, well now let's send out an explorer in the other direction, and this time the square root of this number will have to be about there, and the square root of this number will have to be about there. And you can see what's going to happen. The square root has to go like that, and when we get to -1, by continuity the square root has to be -I. So we seem to have a contradiction. We've managed to prove that the square root of -1 should be I, and we've also managed to prove that it should actually be -I. And how do we fix this? Well, the answer is there is no way to fix this. There is simply no way to define the square root of all complex numbers in a continuous fashion. And this is just a real nuisance, and there's nothing very much we can do about it. It's just a problem we have to live with. You notice the problem is caused by the fact that whenever you go round the origin, the argument of a complex number in some sense increases by 2 pi, so half the argument will increase by pi. And this means that if you try and define the square root on any loop that goes around the origin, when you come back, you will find you've got minus the thing you thought was the square root. So it's kind of like, you occasionally get these science fiction stories or movies where you go around a black hole or something, and you come back into an alternate version of your universe where everything is slightly different. And you can think of the origin as being something like a black hole, where if you go round it, you come back into an alternate universe where all the square roots have mysteriously changed signs. So if you started at 1 and went all the way around here trying to keep the square root continuous, when you got back to 1, you would suddenly discover the square root of 1 had become minus 1 instead of 1. You will sometimes see the phrase multi-valued function used for things like this. So you will sometimes see that the square root is a multi-valued function because it has 2 different values. Well, the trouble is there is no such thing as a multi-valued function. I don't really like this terminology because functions by definition only have 1 value, and a multi-valued function is a sort of oxymoron. So what the phrase multi-valued function means is it doesn't mean you've got a function that's multi-valued. It's a sort of shorthand form of saying that if you try and define a function, you run into weird problems. I mean, you can define several different functions. For example, I could define a perfectly good square root function in this region here, or in this region here, or in this region here, and I can sort of piece them together locally, but I can't define a single function globally. So multi-valued function is just a way of saying you don't really have a function and need to be a little bit careful about it. So that's done square roots. What about other roots? Well, other roots we can do in much the same way. So we can also find the nth root of z, and I'll just do a sort of example, and I'm going to do an example graphically. So as usual, let's draw in the unit circle to give a sense of scale, and let's try and figure out what is the 5th root of 4 plus 3i. Well, as you may suspect, there's going to be more than one 5th root. So let's just try and draw it diagrammatically. So here we take the point 3 plus 4i. And now we have to work out its argument and its absolute value. So what we do is we take the argument, theta, and we divide it by 5, so that when we multiply it by 5 again, we'll get back to what we first thought of. So here we have an angle theta over 5. So the 5th root is going to lie somewhere on this line. And now we have to take the 5th root of the absolute value. Well, the absolute value of 3 plus 4i is, I guess it's 5 by Pythagoras. So we take the 5th root of 5, which is going to be somewhere down here. So we want the r to be the 5th root of 5. And so we take this point here. So here we take the point z, and we have z to the 5 is 4 plus 3i, where z is equal to the 5th root of 5, and its argument is 1/5 of theta. Well, just as numbers have more than one square root, they also have more than one 5th root. In fact, you see, if we've got this angle theta over 5, we could also take theta plus 2 pi over 5, because this number also has argument theta plus 2 pi, and it has argument theta plus 4 pi, and so on. So what happens is we get the argument of the 5th root is not really well defined, because we can add 2 pi over 5 to it, or we can add 4 pi over 5 to it, or we can add 6 pi over 5 or 8 pi over 5 to it. And what you see is what we get is a nice regular pentagon. except this isn't a nice regular pentagon because I'm not very good at drawing. But here are the 5 roots. That they lie on a regular pentagon. And the same happens if you take any nth roots of any non-zero complex number. You find there are going to be n roots, and they lie on the vertices of a nice regular n-sided polygon, and you can work out the vertices explicitly by working out the argument and the absolute value of z and dividing the argument by n and taking the nth root of the absolute value. So what we've shown is that any complex number z has an nth root. In fact, if z is non-zero, it's going to have n distinct nth roots. Z equals 0 is a little bit funny, of course, because it doesn't really have a well-defined argument. What this means is the polynomial z to the n minus a always has a root. More generally, we can ask, do more complicated polynomials have roots? For instance, if we take z to the n plus a n minus 1, z to the n minus 1 plus a n minus 2, z to the n minus 2, and so on all the way down to plus a1z plus a0. Suppose we want to solve this equation here. And well, it turns out that this always has a complex root. We're not going to prove this lecture, but the proof should be appearing in a few lectures' time when we've done Liouville's theorem, which allows us to give a one-line proof of the fact that any polynomial always has a complex root. We sometimes express this by saying the complex numbers are algebraically closed, or is algebraically closed. So algebraically closed just means that if you've got any non-constant polynomial, you can always find a root of that polynomial. So for the last application of this geometric way of looking at multiplication, let's look at the multiple angle formulas. So you know there are formulas for cosine 2 theta equals cosine squared theta minus sine squared theta. And cosine of 3 theta is equal to cosine cubed theta minus 3 cosine theta sine squared theta, which you can also write as 4 cosine cubed theta minus 3 cosine theta, and so on. And you can, of course, work out these formulas by doing some slightly tedious algebra using the formulas for multiple angles. But using complex numbers, there's a very quick way of getting all these formulas without really doing very much work. In fact, you can get them from the binomial theorem, and the trick is as follows. You write cosine n theta plus I sine n theta is equal to cosine theta plus I sine theta to the power of n. That's just because addition of angles corresponds to multiplication of complex numbers. So raising a complex number to a power of n just corresponds to multiplying its angle by n. And now we can expand this by the binomial theorem. So this is cosine theta to the n plus n cosine theta to the n minus 1 sine theta times I. Remember the I. And then we get a minus cosine theta to the n minus 2 sine theta squared, and we should multiply that by the binomial coefficient, which I forgot to leave room for, and we've got a minus 1 because this is just I squared, and so on. Well, how do we extract a formula for cosine n theta from this? Well, we can just take real parts of both sides. So this is a complex number which is a real number plus I times a real number. So the real part will just be the real part of this. So we find cosine of n theta is equal to cosine theta to the n minus n choose 2 cosine theta to the n minus 2 sine squared theta sine theta squared plus various other terms which I'm feeling much too lazy to write out. So I'll just do this for n equals 5 as an explicit example. So we have cosine of 5 theta plus I sine of 5 theta is then equal to cosine theta to the 5 plus 5 cosine theta to the 4 times sine theta times I plus 10 minus 10 cosine theta cubed sine theta squared minus 10I times cosine theta squared sine theta cubed plus 5 times cosine theta sine theta to the power of 4 plus 5I times sine theta to the 5. So if I want to work out cosine of 5 theta, all I have to do is to take the following terms. So we have that cosine 5 theta is going to be the real part of this. So we get a cosine theta to the 5, that's imaginary. Then we get this term here, and then we get this term here. So that gives the multiple angle formula for cosine 5 of theta. Okay, so next lecture we'll just be reviewing cosine and sine. Well, we've been doing cosine and sine for real values here, but what we want to do is to find the cosine and sine of a complex number, and we also want to find the exponential of a complex number, and it turns out that these are actually the same problem because we can write cosines and sines in terms of exponentials.